On May 25, 2026, a group of engineers walked into a semiconductor symposium in Shanghai and did something that defied the modern rules of geopolitics. They didn't unveil a faster processor. They didn't announce a massive multi-billion-dollar factory. Instead, they published a new law of physics. They called it the Dow scaling law, and they claimed it would completely replace Moore's law, the 60-year-old equation that built Silicon Valley and dictates the speed of every smartphone, data center, and supercomputer on Earth. To understand how bizarre this is, you have to understand the sheer scale of what they are challenging. Moore's law isn't just a guideline. It is the economic engine of the global tech industry. For 6 decades, it has promised that the number of transistors on a microchip doubles roughly every 2 years, making computers twice as fast and twice as efficient. Apple, Google, Nvidia, the internet itself, everything runs on this race schedule of shrinking hardware, and a company that the West spent the last 6 years trying to isolate just declared it dead. Go back to 2019. That was the year the United States put Huawei on an entity list, effectively cutting them off from the lifeblood of advanced technology. They were banned from buying American chips, blocked from using American software, and entirely cut off from the most advanced manufacturing equipment on the planet. The goal in Washington was unambiguous: freeze them in time. The sanctions were designed to push them so far behind the cutting edge that they could never catch up. By 2022, the restrictions tightened even further, pulling in Dutch and Japanese suppliers. Every door to the future was locked and sealed, and yet 6 years later, they didn't just find a way around the wall. They claimed to have bypassed the next decade of chip development entirely by rewriting the rules everyone else is still playing by. Here is the part that should stop you cold. This wasn't a vague corporate press release filled with marketing buzzwords. They published the mathematical framework. They laid out a peer-reviewable roadmap showing how, by 2031, this new law will allow them to build chips that match the performance of the most advanced processors on Earth. And they plan to do it using the exact generation of manufacturing tools that the United States banned them from upgrading. For the first time since the dawn of the digital age, the fundamental law defining how computing progresses was written in Chinese, not English. To see why this has sent shockwaves through the global semiconductor industry, you have to look at the sheer physical absurdity of the mountain the rest of the world is currently climbing. Right now, the cutting edge of chip manufacturing relies on making transistors smaller. We are currently down to the 3-nanometer scale. To put that into perspective, a single nanometer is 1/1000th of a meter. A strand of human DNA is about 2.5 nanometers wide. The structures being etched onto modern silicon are smaller than the wavelength of visible light. We are quite literally trying to manipulate matter at a scale where light itself cannot resolve the shapes we are creating. The only way the Western world knows how to do this is by using extreme ultraviolet lithography machines, built exclusively by a single company in the Netherlands called ASML. Each machine is a marvel of human engineering. They cost over $300 million each, weigh as much as a commercial airliner, and require a fleet of cargo planes just to transport. They use explosions of molten tin droplets to create specialized plasma that reflects a light beam into a mirror polished to an accuracy of a few atoms. It is arguably the most complex manufacturing process ever invented by humanity, and it is a process that Huawei is legally forbidden from buying into. So when your back is against a wall of that magnitude, you have two choices. You can spend decades and hundreds of billions of dollars trying to replicate a machine you aren't allowed to have, or you can ask a question that sounds like absolute madness to the rest of Silicon Valley. What if the entire world has been solving the wrong problem for 60 years? When the semiconductor industry became obsessed with size, it forgot the fundamental physics of why smaller transistors actually make a chip faster. The industry assumed that shrinking the physical gate was the only way forward. But the engineering team behind this new paper realized something else. The true bottleneck in modern computing isn't just the physical size of the switch. It's the time it takes for an electrical signal to travel between those switches. In physics, this time constant is represented by the Greek letter tau. Every electrical engineering student learns about it, but for generations, the industry treated it as a fixed, unchangeable property of standard materials. You shrunk the transistor, and tau naturally got smaller as a byproduct. But as we approach the physical limits of atoms, shrinking transistors causes massive problems. Electricity starts to leak. Quantum tunneling takes over. The chips get too hot, and the performance gains vanish. We are hitting a literal wall of physics. The Tau scaling law flips the entire equation on its head. It treats the signal propagation time, tau, as the primary variable independent of transistor size. Instead of spending billions trying to shrink a transistor from 7 nanometers down to 2 nanometers, the new framework focuses entirely on 3 radical pillars. First, a concept called logic folding. Instead of spreading circuits across a flat piece of silicon, they stack them vertically in ultra-dense, multi-layered sandwiches, dramatically shortening the physical distance a signal has to travel. Second, they completely re-engineered the materials between the transistors, focusing on new conductors and insulators designed specifically to accelerate the speed of the electrical signal itself. Third, they completely threw out traditional circuit geometry, rewriting the wiring pathways so that the longest signal path on a chip is drastically reduced without changing the size of a single transistor. The theoretical numbers they published are staggering. A 41% increase in power efficiency and a 55% reduction in the total number of transistors required to hit the exact same performance targets as Western chips. Under the rules of Moore's law, matching a 1.4 nanometer chip using 7 nanometer equipment is mathematically impossible. Under the Tau scaling law, it is a matter of geometry and material science. This isn't just a clever engineering workaround. It represents a fundamental shift in the global balance of technological power. Think back to the mid-20th century. America became the undisputed tech superpower, not because it made the best consumer products first, but because institutions like Bell Labs wrote the foundational mathematics of information theory and invented the transistor itself. They wrote the rules that the rest of the world had to follow for 70 years by publishing a peer-reviewed open framework. This announcement mimics that exact strategy. It invites the global scientific community to stop looking at transistor size and start looking at signal velocity. It forces every major player, from NVIDIA and Intel to TSMC and Samsung, to download these papers, audit the math, and decide whether they are currently spending hundreds of billions of dollars climbing the wrong mountain. The implications are dizzying. It leaves the global tech industry facing an incredibly uncomfortable reality. If the math holds up, the decades-long Western monopoly on the rules of computing just evaporated. But a theory on paper is one thing. Proving it works in the messy, brutal reality of mass production is another entirely. Can a company under total economic siege actually manufacture the future? Or have they simply found a brilliant way to disguise a desperate technological dead end? To understand exactly how this new framework works, we have to stop looking at microchips as flat, two-dimensional maps and start looking at them as massive, hyper-congested megacities for the last 60 years. The entire semiconductor industry has built chips using a design philosophy that is essentially a sprawling, single-story suburb. Imagine a city where every house is a transistor and every road is a copper wire connecting them. Under Moore's law, if you wanted to build a more powerful city, the solution was simple. Make the houses smaller so you could cram more of them into the exact same county lines. At first, this worked beautifully. The houses got smaller, the roads got shorter, and the people, or in this case the electrical signals, could zip from house to house at incredible speeds. A 90 nanometer city became a 45 nanometer city, then a 14 nanometer city, and finally, today's cutting edge, a 3 nanometer metropolis. But as the houses shrank to the size of a few dozen atoms, a catastrophic problem emerged. The houses are now so close together that the walls are literally disappearing. The electricity meant to stay inside. One house starts leaking into the neighbor's yard through a bizarre physical phenomenon called quantum tunneling. To stop this leakage, engineers had to build incredibly complex, expensive microscopic fences. Worse, because you have billions of these tiny houses crammed onto a flat piece of silicon, the size of a fingernail, the traffic on the roads is gridlocked. The chip starts overheating, not because the transistors are slow, but because the signals are stuck in bumper-to-bumper traffic. This is where the Tau scaling law changes everything. Instead of trying to make the houses even smaller, a task that requires those $300 million ASML machines, the new framework looks at the city and says, stop shrinking the houses. Start building skyscrapers. The first pillar of this mechanism is what the engineers call logic folding. Think of a standard 7 nanometer chip as a long, flat piece of dough. If you want a signal to get from one end of the dough to the other, it has to travel the entire length of the surface. Logic folding literally takes that piece of dough, folds it in half, and stacks it on top of itself. Suddenly, two circuits that used to be on opposite sides of the chip are now sitting directly above and below each other, separated by a fraction of a micrometer. To connect them, engineers don't use long, horizontal surface roads anymore. They drill vertical elevator shafts directly through the silicon. In advanced packaging, these are known as through-silicon vias, or TSVs, but the Dow law optimizes them at a foundational architectural level. By turning a massive, sprawling suburb into a tightly packed, multi-story apartment complex, the physical distance a signal has to travel drops by orders of magnitude. You have achieved the speed of a 2-nanometer chip while using 7-nanometer houses, but vertical stacking creates a secondary crisis: heat. If you stack multiple layers of hot processors on top of each other, the chip will quickly cook itself to death. That brings us to the second pillar of the mechanism: treating the time constant, tau, as an independent material science problem. In traditional physics, the speed at which an electrical signal propagates through a circuit is dictated by two main factors: resistance and capacitance. Resistance is how hard it is for electricity to push through a wire. Capacitance is how much electrical charge that wire accidentally stores along the way, acting like a tiny sponge that slows down the flow. Together, they create what engineers call the RC delay. For decades, Silicon Valley accepted the RC delay as a fixed tax of using standard materials like copper and silicon dioxide. The Tau framework systematically replaces these materials with an entirely new atomic buffet. By utilizing ultra-low K dielectrics, specialized insulating materials filled with microscopic nanopores, they prevent the wiring from soaking up electrical charge like a sponge. At the same time, they introduce highly optimized interface layers between the metal and the semiconductor. It is the molecular equivalent of replacing a gravel road with a frictionless sheet of ice. The transistors themselves aren't any smaller, but because the electrical current can glide through the channels with almost zero resistance, the time constant, T, plummets. The signal moves faster, the traffic clears, and the heat generation drops by 41%. The third and final pillar is perhaps the most elegant, because it doesn't require any new materials at all. It is pure topological mathematics. In any microchip, the overall speed of the processor is bottlenecked by its slowest path. This is known as the critical path. Think of it like a relay race where a team of runners has to pass a baton. If 3 of your runners are Olympic sprinters, but your 4th runner is carrying a heavy suitcase across an unpaved field, your total race time is going to be terrible. In modern chips, the critical path is often a tortuous, winding route that a signal must take to coordinate actions between the logic cores and the memory. The Tau scaling law introduces an algorithmic layout system that dynamically rewrites the geometry of these connections. By using advanced graph theory and machine learning models during the design phase, the framework identifies every potential critical path on the chip and systematically flattens the wiring layout. It ensures that the longest, most tortuous signal path is drastically shortened. The Olympic sprinters no longer have to wait for the runner in the mud. The entire relay race is synchronized perfectly when you synthesize these 3 pillars: logic folding, material optimization, critical path flattening. Something extraordinary happens to the math. You break the tyranny of the nanometer nomenclature. For years, the term nanometer in the tech industry hasn't actually referred to the physical size of anything on the chip. It has become a marketing shorthand for performance equivalence. When a company claims they are making a 3-nanometer chip, nothing on that chip actually measures exactly 3 nanometers. It just means the chip performs at a level we expect from a hypothetical 3-nanometer breakthrough. Huawei's framework proves that you can achieve that exact same performance equivalence without playing the shrinking game. By manipulating the time constant T through architecture and material physics, a 7-nanometer node can deliver the density, latency, and power metrics of a 1.4-nanometer node. It is a loophole in the laws of scaling that the West assumed was impossible without extreme ultraviolet lithography. But this elegant theoretical architecture immediately runs into a massive, glaring paradox. If this physics-defying shortcut is purely an architectural and mathematical victory, it raises an uncomfortable question about the rest of the global supply chain. Why did the brilliant minds at TSMC, Intel, Samsung, its firms staffed by the greatest engineering talents on Earth, spend hundreds of billions of dollars chasing smaller transistors into a quantum dead end if they could have simply rewritten the geometry of the chip from the start? What did the Western chip giants know about this approach that made them avoid it for decades? To find out why the rest of the world ignored this shortcut, you have to realize that the global semiconductor industry didn't stumble into its current position by accident. It followed the money. For 60 years, the economics of Silicon Valley were beautifully predictable. If you were Intel, AMD, or Apple, you didn't need to completely reinvent chip architecture or overhaul your material science every 2 years. You just waited for the factories, the massive foundries like TSMC, to shrink the transistors for you. It was an assembly line of progress. It made more sense to spend billions buying smaller gates than to spend billions rethinking the math. The entire Western ecosystem became optimized for a single, linear path, geometric scaling. But when the United States cut off Huawei's access to that assembly line, they didn't just strip away a vendor, they inadvertently broke the economic spell. Under extreme constraints, the luxury of linear thinking disappears. You can no longer afford to solve problems by throwing capital at bigger, more precise machines. You are forced to look at the foundations of the science itself. The strategic implication of the Tau scaling law goes far beyond a single company beating a trade ban. This is a structural pivot that could alter the entire trajectory of the global AI race. Global Semi-Research Substack right now, the geopolitical battle for artificial intelligence is being fought over sheer volume. Tech giants are building data centers that consume as much electricity as small cities, packing them with hundreds of thousands of identical, ultra-expensive processors. The underlying assumption is that whoever owns the most 3-nanometer or 2-nanometer silicon wins. But the Dow framework shifts the metric of victory from the size of the transistor to the efficiency of the system. CRN Asia by introducing Unified Bus, a new interconnect protocol that allows thousands of these optimized processors to share memory instantly. They have created what they call superpods. In a traditional AI cluster, individual chips spend a massive amount of time waiting for data to travel across external cables from separate memory banks. It is the equivalent of a brilliant researcher having to walk to a library in another town every time they need to read a single sentence. Unified Bus turns the entire data center into a single, cohesive brain where every processor possesses native memory semantics. The communication latency doesn't just drop, it virtually disappears. TechSauce Show 1. This reveals the ultimate irony of the modern tech embargo. By attempting to freeze China at the 7-nanometer node, the sanctions forced Chinese engineers to pioneer system-level co-optimization decades before the West intended to seriously explore it. While Silicon Valley is still burning through hundreds of billions of dollars to squeeze the last few remaining atoms out of traditional silicon, this new roadmap focuses heavily on advanced packaging and spatial reorganization. Car News China. The market consequence of this shift is immediate. Later this year, in the fall of 2026, the first commercial test of this law will hit the consumer market inside the new Kirin smartphone processors. If those devices deliver the promised 55% jump in density and 41% power efficiency while running on 7-nanometer hardware, the marketing narrative that has driven smartphone sales for a generation will collapse. Consumers will realize that a nanometer is no longer a measure of physical superiority, but a legacy metric of an aging paradigm. TechSauce. We are witnessing the fracturing of a unified global tech ecosystem into two completely distinct ideological camps. One camp is backed by the immense capital and institutional inertia of the West, committed to pushing Moore's Law to its absolute physical graveyard using extreme ultraviolet lithography. The other camp is driven by necessity, constructing an alternative paradigm out of pure topology, material engineering, and stacked logic. It is a classic underdog paradox. The very restrictions meant to guarantee Western technological dominance have accidentally created a competitor that no longer needs the West's most guarded tools. By shifting the battlefield from advanced machinery to architectural intelligence, the rules of the entire century are being rewritten. The question is no longer whether an embargoed nation can catch up to the cutting edge. The question is whether they have just rendered the cutting edge completely obsolete. This brings us back to that room in Shanghai, where a legacy equation was quietly set aside. For over half a century, the story of technology was written as a race toward the microscopic. The winners were always the ones with the sharpest tools, the biggest budgets, and the most advanced factories. We were told that if you lose access to those tools, you lose the future. But history has a strange way of punishing predictability. When Gordon Moore first noted that transistors would shrink at an exponential rate, he wasn't declaring a permanent law of nature. He was describing a specific, highly profitable business model that worked flawlessly as long as the physics remained simple. The moment that model hit a wall of quantum interference and soaring costs, the industry didn't stop. It just ran out of easy answers by forcing a massive, well-funded engineering ecosystem into total isolation. The trade sanctions didn't halt progress, they simply broke the inertia of the old design philosophy. The Tau scaling law is the direct result of that break. It is a stark reminder that in the theater of global innovation, absolute scarcity can be a far more potent fuel than unlimited capital. If this new roadmap achieves its targets by 2031, the global map of technology will be fundamentally inverted. The intellectual center of gravity for the next generation of chip design will no longer reside exclusively in Silicon Valley or Eindhoven. Future engineers will calibrate their systems using mathematical variables defined by a company that was written off as dead 6 years ago. They will design multi-layered, folded logic architectures because that will be the only way to remain competitive in a world where physical shrinking has reached its absolute atomic limit. The great irony of this modern tech war is now fully visible. The sweeping embargoes designed to preserve a Western monopoly on the future may have accidentally accelerated its conclusion. In trying to lock an adversary out of the modern digital age, the world's leading tech superpowers may have simply forced them to build the next one. We often look at technological progress as a straight line, a ladder where the person on the highest rung always stays ahead. But true innovation rarely moves in a straight line. It twists, it loops, and occasionally it hops to an entirely different ladder while everyone else is still looking up. The next time you look at the smartphone in your hand, or hear about a new multi-billion-dollar semiconductor factory being built in the desert, remember that the true power of technology doesn't lie in the size of the machine that carved the silicon. It lies in the framework of the mind that directed it. The race was never about who could build the smallest switch. It was always about who could find the shortest path for the mind to travel. As the old laws of computing finally fade into history, we are about to find out who is truly writing the rules of the next 50 years.